our last worksheet is finishing up linear systems of ODEs, solving by finding eigenvalues and eigenvectors. And for worksheet 12, we're going to look at special cases. And our special cases are repeated eigenvalues, and then we're going to look at complex eigenvalues. So our steps for solving a system of linear differential equations using eigenvalues and eigenvectors are up here. Step 1 is to write the system in matrix form, and then step 2 is to find the eigenvalues, lambda, that solve the equation. We have the determinant of our coefficient matrix A minus lambda times the identity matrix. This subtracts lambda across the diagonals is equal to 0. That gives you solutions to that, will give you eigenvalues. And then you use those eigenvalues to find vectors that solve the equation A minus lambda I times some vector V is equal to 0. And the solutions then were in the form x1 is equal to v1 e to the lambda t, lambda 1t, and x2 equals v2 e to the lambda 2t, and so forth, where your general solution is c1 x1 plus c2 x2 plus, and so on. For the most part, we're working with 2x2 systems or 3x3 systems. On the worksheet, I only have 2x2 systems, but in the homework assigned from the textbook, there are some 3x3 systems also. So with repeated eigenvalues, you want to suspect that just like with the higher order linear differential equations, you're going to get a second linearly independent solution by multiplying the previous solution by t. And you get something very similar to that here. If our first solution is v1 e to the lambda 1t, then our second solution is going to have k is going to be some vector, but notice we get the t e to the lambda 1t, which is just multiplying x1 by t and not looking at this vector. You get the t e to the lambda 1t, and you also get an e to the lambda 1t. With repeated eigenvalues, if you have a larger than 2x2 system, then it may be possible to find two linearly independent eigenvectors. If you do have two linearly independent eigenvectors, then you could have two solutions that look like they'll both be e to the lambda 1t, but you have two different eigenvectors multiplied. Now with the 2x2 system, this is almost never happens, but with the larger systems, it is possible. And you do have at least one homework problem where you do find linearly independent eigenvectors associated with a single eigenvalue. So let's solve a system that has repeated eigenvalues, and then we'll look at how we can solve for our eigenvectors k and p. Okay, so here in matrix form, this system becomes I'll write it over here. X prime is equal to, in my first row I have coefficients of -6 and 5. In my second row I have coefficients of -5 and 4 times x. So to find my eigenvalues, to find lambda, I want to solve the determinant a minus lambda I is equal to 0. So a minus lambda I is going to subtract off lambda from the diagonal. It's going to give me -6 minus lambda, 5, -5, and 4 minus lambda. If I multiply this out, if I take the determinant by multiplying the diagonals, I'm going to get -6 minus lambda times 4 minus lambda, and then minus 5 times -5 minus a 25. And then simplifying, here I get lambda squared. I have a 6 lambda minus 4 lambda. That's going to give me a 2 lambda minus 24 plus 25. And the minus 24 and the plus 25 combines to give me a +1. So notice that lambda squared plus 2 lambda plus 1 factors into a perfect square. You get y plus 1 squared, or you get lambda equals -1 multiplicity 2. When lambda is equal to -1, you can find your eigenvector by solving a minus -1i, that's the same as a plus 1i times some vector is equal to 0. This adds 1 across the diagonal. So if I take my coefficient matrix and add 1 across the diagonal, I get -6 plus 1, that gives me -5, -5, and then here 4 plus 1 gives me a 5 times v, and I'll write that as v1, v2 is equal to 0. So notice that both of these rows give me the same equation, -5 v1 plus 5 v2 equals 0, and my second row gives me the same thing, -5 v1 plus 5 v2 equals 0. I'm going to solve for v2. I'll bring the v1 over. That gives me 5 v2 is equal to 5 v1, and then divide by 5, and we get v2 is equal to v1. And so I'm going to choose my vector so that v1 and v2 are the same. You can choose any numbers you want, but most of the time we want to stick with nice numbers, nice small numbers. Don't choose 0, but choose 1. If you have fractions, choose a number to get rid of the fraction. So v is equal to 1, and we have one solution is our eigenvector times e to the lambda t, where lambda is -1. One solution is x1 is our vector 1, 1 times e to the -t. Because both of these equations gave me the same equation, and with the 2 by 2 system you always essentially get the same equation back. What we want to do is construct a second solution. And we want to construct a second solution so that if this is my vector k, I just want to match the notation on the other page so that when I come back here, a minus lambda I times k, I'm sorry, times p, some new vector p, is equal to k. And again, these are vectors. And in this case, lambda is -1. So I want to construct a solution, and before I go on, the equation that we're using here, a minus lambda I times p is equal to k, the derivation for this equation is given in your textbook. You can look in the textbook and determine how that comes about. Anyway, let's go ahead and solve it. A minus lambda I times p is equal to k. Here, lambda is -1, so I'm again adding 1 across the diagonals, and I'm going to end up with -5, 5, -5, 5. Times p, that's a vector, and I'm going to call that p1, p2, is equal to this previous vector that I found, k, which is 1, 1. Now, if I write this out as the system, I'm going to get -5 p1 plus 5 p2 is equal to 1. And my second equation is going to give me the same thing. -5 p1 plus 5 p2 is equal to 1. So here I'm going to solve for p2. I can bring my p1 term over to the right side, so I get 5p2 is equal to 1 plus 5p1, and then divide by 5, and I get p2 is equal to 1 plus 5 p1 over 5. So here I want to choose values. Normally you want to choose a value that will cancel out the denominator, but it's really not possible to choose one. And so I'll just choose 1 for p1. And if p1 is 1, then I get 1 plus 5 is 6 over 5 for p2. And I get this vector, 1 and 6/5. So our second solution is going to be, let me look back to see the form that I need to have it in. It's going to be k is the original vector that we came up with from the first solution. You multiply by t. So you've got the previous solution just multiplied by t, and then you have p times that exponential. So I'm going to get my previous solution, which is here, x1, 1, 1, but multiplied by t, t e to the negative t, plus, and then I get 1 6/5 e to the negative t. My general solution is c1x1 plus c2x2. And so my general solution here is c1 times 1, 1 e to the negative t plus c2 times 1 t e to the negative t plus 1/6 e to the negative t. If we had initial conditions, we'd go ahead and solve for them, but here we don't have initial conditions. Okay, and our last example is this system where we will end up with complex eigenvalues. And so we're going to get eigenvalues in the form of alpha plus or minus beta I. And if we just take the positive eigenvalue, alpha plus beta I, we will be able to come up with two vectors. B1 is 1/2 K1 plus K1 bar. This K1 bar is a complex conjugate. It's a conjugate of K1, where K1 is the eigenvector that corresponds to this eigenvalue that we get. And so if we add K1 to its conjugate, then we're going to get only the real parts. So this is actually also called the real part of K1. You're going to be adding the real parts because the imaginary parts will drop out. And you're going to add the real parts twice and then divide by 2. So this is the same as the real part of the eigenvector. And then here, if you multiply K1 by negative and then add the conjugate, here the real parts will drop out. And you're going to get just the imaginary parts. And that negative will make it negative you're going to get the opposite of twice the imaginary. And if you multiply by I, you're going to get an I squared, which is a -1. It's going to cancel out the negative and divide by 2. It gives you just the imaginary part of that eigenvector. So rather than using these formulas, B1 is 1/2 K1 plus K1 bar, and B2 is I over 2 times negative K1 plus K1 bar, we could just say that B1 is the real part of the eigenvector and B2 is the imaginary part of that eigenvector. Notice that our solutions are a little bit complicated also. You can imagine with imaginary eigenvalues, you end up with sines and cosines. So you have cosine beta t, sine beta t, and the real part, the alpha, gives you the exponential e to the alpha t. But then you've got this real part and this imaginary part multiplied by sines and cosines. For the second solution, that real and imaginary part switch places, and there's also a little negative built in there. So let's go ahead and solve the system. I'll start by writing the system in matrix form. I have x prime is equal to, and my coefficient matrix is 1, -8, 1, -3 times x. So to find lambda, I'm going to solve the determinant a minus lambda I is equal to 0. And a minus lambda I gives me 1 minus lambda, and -8 in the first row and then 1 and negative 3 minus lambda in the second row. If I take this determinant, I get 1 minus lambda times negative 3 minus lambda minus negative 8 and if I expand this, I'm going to get lambda squared. Here I get a negative lambda and a positive 3 lambda. That's going to give me a positive 2 lambda minus 3 plus 8 gives me lambda squared plus 2 lambda plus 5, and that's equal to 0. Now, lambda squared plus 2 lambda plus 5 doesn't factor. I'm going to solve this by completing the square. I'm going to start by bringing this 5 over to the right side. Gives me a negative 5. And then with the lambda squared plus 2 lambda, I'm going to complete the square by taking half of 2 and squaring it. Half of 2 is 1. Squaring it gives me a 1. I'm going to add 1 to both sides. Lambda squared plus 2 lambda plus 1 factors into lambda plus 1 squared equals negative 4. Get rid of the square by applying the square root property to both sides. You get plus or minus the square root of negative 4, which gives you plus or minus 2i, and then solve for lambda. We get lambda is negative 1 plus or minus 2i. Okay, now to find the eigenvector, you really only have to find one eigenvector. You don't have to use lambda equals negative 1 plus 2i and lambda equals negative 1 minus 2i. I'm going to use just the plus 2i. And now we want to solve a minus lambda I times k is equal to 0, where a minus lambda I, we're subtracting off negative 1 plus 2i across the diagonal. So I'm actually adding 1 and subtracting 2i. That's going to give me a 1 plus 1 will give me a 2. Subtract off 2i. And here adding 1 gives me a negative 2. And then minus 2i times k equals 0. When I write out these equations, I'm going to get 2 minus 2i times k1 minus 8 times k2 is equal to 0, and 1 k1 plus negative 2 minus 2i times k2 equals 0. This system is going to be dependent, and you could prove that it is by trying to cancel it out. But what I'm going to do, I know that it's going to be dependent, is I'm going to just solve this second equation for k1. When I bring the k2 term over, both of these numbers, the negative 2 and the negative 2i, become positive. And then I'm going to choose my vector k, so that k2 is 1. And then k1 is going to be 2 plus 2i times 1. And so notice that k, I'll bring that over here, can be written as the vector 2, 1 plus the vector 2, 0 times I. So we've got our real part and we have our imaginary part. Okay, so our B1 is this vector 2, 1, and our B2 is this vector 2, 0. Okay, and we get solutions. X1 is, and up here I'm looking at our solutions. X1 is B1 cosine beta t. So I have B1 is the vector 2, 1 cosine beta t, and beta is the imaginary part of our eigenvalue, is 2. Cosine 2t minus b2, which is a vector 2, 0, sine beta t, multiplied by e to the alpha t. Alpha is negative 1. So I get multiplied by e to the negative t. And my second solution is b2 cosine beta t. b2 is this vector 2, 0 cosine 2t plus b1 sine beta t. b1 is a vector 2, 1. I get sine 2t e to the negative t. And our general solution, I'm not going to write it all out, but is c1 x1 plus c2 x2. So put all this together for our general solution.